Hey, what's up, guys? Okay, so in this video, I want to share a very cute and small example, and and it goes through the detail. Right. So in the probability theory, people want to ask the following question: Suppose I give you like two random variable, and I say that they all have the same moment for all zero moment, first moment, second moment, and up to infinite. So we say that these two variables has the same a moment, and then I want to ask whether x the same as y. And then you can like spend some time find definition of equal, right? But I guess the intuition asks whether the probability of x greater or equal to a is the same as probability of y greater or equal to a for a. Basically, we are asking whether they are the same as the probability distribution. And the amazing question is that answer is no. Okay, the answer is no. Okay, and you can go through a lot of textbook, but some of the few of them provide example, right? So in this video, let's go through example. Okay, so these are the common example. The first one is this f1 is 1 over 2 pi x divided by times exponential of this. This is a standard called the log normal distribution. Okay. And the one interesting thing is that it's very interesting. It's very trivial to show that f1 is valid. Is a valid probability distribution. Okay, let me just tell. So f1 is valid PDF. Okay, and the reason is that obviously the f1 is greater than 0, and if we do the trivial integration, dx, let's say y equals to log x, so we get infinite and negative infinity, and the square root of this. So notice that this means that exponential y is x, so exponential y dy is dx. So that means that dx divided by x is the same as dy. Okay, so now this is dy exponential negative y squared divided by 2. Okay, and this is Gaussian integral. Okay, so using your trivial Gaussian integral elementary calculus to prove this one. Okay, so f1 is a very probability distribution, and you can take f2 to be f1 times 1 plus sine 2 pi log x. Okay, and it's very interesting it's trivial to see that f1 different from f2 for uncountable x. Right, so obviously the f1 and f2 are different probability distribution. Right, if you plot it, you will see f1 is like, I guess this f1, and the f2 is f2 will be like somehow like this. There's f2. Okay, so and also obviously the f2 is also a very probability distribution. Okay, so let's check. Right, so let's check. f2 is divided by f1, 1 plus sine 2 pi log x. Let's say so f2 is also valid PDF. Okay, so the first one is that f2 is greater or equal to 0 trivially because sine is at most -1, right? And now let's go through this integral. So as we previously defined, right? So let's write down the definition. Dun, dun, dun. So it's like 1 plus sine 2 pi log x dx. Okay, so we do the same change of, right? So we just need to show, right? We just need to show what? Show this guy is 0. Okay, and it's almost trivial, right? So let's do the same thing. Let's write log x equals to y. So x is exponential y. So dy is equal to dx divided by x. Okay, so what we have is this guy, minus y squared divided by 2 times sine 2 pi y dy. Okay, so this is 0, right? Because the reason is that this guy is odd. Right? If you change y to negative y, right? Then this is the same. This has a negative sign, right? So this guy is an odd function. Okay, and then you can trivial prove that this is this. Okay, so it's 0. Okay, so f2 and f1 are the same. it's a valid probability distribution. Okay, so finally, I want to say that, but if I calculate all the moment, they are the same. So what I'm saying is that if I calculate, if I calculate all the moment, all the positive greater or equal to 0 integer moment, then this guy is exactly the same as this guy. Okay, so this so this means that then F1 and F1 makes become a counterexample. Counterexample. Okay, of previous statement. Okay, and so let's go through this proof. Okay, and this proof is trivial by this proof can be proved by just check the following. Okay, so let's check the following. Right. So in order to prove it, we just write down definition, and all we need to prove is the extra term 0. Right. So it's sine 2 pi log x xr dx 0. Okay, so in the previous, what we have shown is r equals 0. This is can be proved. Okay, so let's go through the proof. So let's write down. Let's try to prove it. Try to compute this, and let's do y equals to log x minus r. So this is infinity negative infinity 1 over 2 pi minus y squared to sine 2 pi. Oh, notice this. Notice this. So now here we have like what exponential y exponential r is x, right? So this is y plus r squared divided by 2 sine of log x, right? So log x is y plus r, right? But r is integer, sorry. So this is sine y, okay? Times x through r, right? X through r. So x through r is exponential yr plus r squared dy. Okay, so now let's compute these two. Okay, so these two is let me just write down. Minus half of y squared plus yr to y 2yr plus r squared plus yr plus r squared sine 2 pi y dy. So this is exponential half of minus y squared minus r squared, and you can see the cross term cancel, right? And yeah, so this is plus, and the sine 2 pi y dy. And it's trivial to see that now this function is r. So r is a constant, right? So I can pull out. So it's trivial to see that this is odd function of y. Because if you change y to negative y, then this sign will give you negative sign, and these are the same. So this guy is 0 for all r greater or equal to 0. Okay, so here that we have shown that these two probability distribution they have the same moment, but they are still different distribution. Okay, so see you guys next videos.